This is Larry. This is day 27 of the May Leetcode Daily Challenge. Let's get started. Hit the like button, hit the subscribe button, hit the whatever button. Leave a comment on how you did. How did you do this farm? Did you enjoy it? Did you hate it? I don't know. We'll see. Possible bipartition. Given a set of n people, we would like to split everyone into two groups of any size. Each person may dislike some other people, and they should not go in the same group. Formally, if dislike sub I is equal to, okay, some dislike edge, you're not allowed to put them in the same group. Return true if it is possible to split everyone into two groups this way. Okay. So yeah, so this is a very standard-ish problem. There are a couple of ways to do it, and you may not even need to understand graph theory for it, but I'm going to explain it with graph theory because for me it comes more naturally. And basically, you have some edges where A dislike B, right? And so what does that mean? That means that if there's, and actually what I would like to, how would I, so basically if for every pair of edges, A and B, that means A and B have to be in a different group, right? And you can kind of start drawing it out by drawing that, okay, well, there's a little bit of a forcing function in this case where, well, this 1 and 2 has to be in a different group. So we could arbitrarily, because it doesn't really matter by the argument of symmetry what group they're in, we have to put 1 in one group and 2 in another group. And then we have another edge that has 1 and 3, then we put 1 with the 1 because it's the same group, and then we're forced to put 3 in another group. So basically, we could kind of use that logic to keep on putting them into two different groups. And then from that, we can construct whether that is true or not. And in more graph theory sense, if it's not a bipartite graph, meaning if there is such a path from A to itself on odd degrees, then it is not possible. So from that, you could actually either use depth first search, or you could use depth first search, you could use union find, you could use breadth first search. There are a lot of different algorithms to kind of play with this. So feel free to explore and maybe solve it in multiple different ways. I'm going to use depth first search just to kind of illustrate how I would think about it, but you could definitely use a couple of things. Okay, so now let's jump right into it. So now, in a way, this feels a little bit greedy in that, or arbitrary, because there's never going to be, yeah, if you have all the edges, you won't get into a situation where, you won't get to a situation where you should have taken a different choice earlier because they're arbitrary. The only thing that may be a little bit tricky is kind of getting the ordering of labeling these vertices, and this is what we will do with depth first search. And let's look at the constraints real quick. N is less than 2,000. There are less than 10,000 edges. Okay, so it's between 1 and n is 1 indexed. Okay, so this sorted from the dislike edges from sort of left and right, and unlike real life, so unrealistic that a person never disliked themselves. But okay, so now I like to set this up given a set of edges, and that's actually maybe something that affects your running time and your complexity in terms of how to thinking about it. Because given a set of edges, maybe you can think of using union find because that, you give me these edges. But for me, I'm okay. I think I'm going to just construct an adjacency list and then do the depth first search as we talked about. Okay, so now adjacency list is equal to, let's just do collections.default dictionary of a list. That means for every element, we will create a list by default. Okay, and then now for each EV and those are terrible names. UV is what I meant in dislikes, and the reason why I put dislikes is, or UV is just that U and V are standard edge names in graph theory. Okay, so now adjacency list of U, append V, and then adjacency list of V, append U, just to kind of keep that symmetric. And then now, let's set up labels. Label, let's go to, let's just say a dictionary. And then now let's say we do a bipartite thing on a recursive, on a certain node X. Yeah. Okay. So now for each recursion, we want to see where it is true or not. So we want to return it if, so okay. So if this is true, if I guess there's no base case. I think I was just thinking about base case, and I think the base case is the case where we're essentially at the leaf of a recursion tree, kind of. But I think that's okay. I think that's just from default. So let's just so our default case is return true if none of the things are false. For yeah. So now we look at each edge. So each outgoing y in adjacency list of x. If label of y is equal to label of x, then we return false. Otherwise, I think we have to do something other things first. Okay, if seen of if not seen is true, then we do a recursion on y. We do some labeling here. Okay. Actually, is just do can construct. Okay, now this goes true, and then can. Something like that. So by default, you can construct is true, but if you haven't seen this y, then we should do a recursion on it. So let's set that to true. Yeah, I guess we could actually just set it here. Actually, let's just use a set. Is it add? Not. Okay. I think this is good enough for the recursion, except for the naming. We'll talk about that later. But now we can do, yeah. Oh, we didn't actually label these, so we're missing something. Okay. So okay, so let's actually put another thing, which is label, current label. Label sub x is equal to label, say, but if x is in labels, that means we already been here, then return label sub x is equal to label. So we try to label it, then we return whether that's already true, because if it's not true, that means that we're messing up somewhere. I think that also implies this, but leaving it in there is fine. Okay, and then we have to change this so that it labels for each edge. You want to label it basically the other parity. So I'm just going to make it from 0 to 0 and 1. So okay. So now we just have to go through for x in, this is not right, this is n, whoops. Okay, so for x in n, or range of n, I think it's just 1 to n. And now I'm just double checking because I remember that this is one base. So I'm just double checking where my code just to make sure that everything is okay with 0 and 1 case, or 1 index, sorry. Okay, so now we just, if not recurse of x, return false, otherwise return true if everything is good for all the inputs. Okay, I think that's roughly good enough, maybe. Oh, I need to put in something. Let me put in the test cases first. So we have to kick off, so that's how we would construct this recursion. The idea is that for each edge with a given label, or each node with a given label, we label all its neighbors on a dislike graph, the opposite of what you're labeling this node, right? I have to start it off, and actually, actually I have to do if x is not in scene, that means we haven't processed yet. And if, okay, this is maybe confusing, so let's just do if not recurse, even though you can just use n, but it's easier to read. Basically, this is saying if we haven't seen x yet, then let's start kicking it off. And you may ask, why is this 0 versus 1 or any arbitrary thing? But the idea is that if you haven't seen the x already, then it just means that this is one tree in the forest. And in that forest, everything is independent from another forest. Or sorry, in that tree, that tree is separate from another tree and another in the same forest. And in that sense, they're independent problems, if you will. And you could check, and you can label them arbitrarily with 0 or 1. So that's why I just chose 0. But it doesn't really matter as long as you start with one of them. So it looks okay. I want to test. Right now I'm thinking about different edge cases that I might be a little bit wrong on. This isn't obviously like a triangle thing. This is a 5. What is it? No. What's a 5 gon? What, 5 gon? Now there's a name for it. Pentagon. There we go. So yeah. So I think 1 maybe a good case, or just like a big number without things. Okay. And I think we could test. In theory, you would want to want some big n's, but as we will analyze in a minute or so, this is linear, so I'm confident that I don't have to test the stress test the big cases because it's linear. You cannot do better than linear in either case. Okay, let's submit it. Okay, cool. Yes. So this is a fun problem for bipartition. I haven't done this in a while, actually, but let's analyze the complexity, the runtime, and the space-time. Runtime and the space complexity. So because of this scene thing, we are guaranteed to only do a recursion on a child or a neighbor edge, or a neighbor through the edge, if it is not seen. And how many times are we going to do this operation, right? Well, so for each node, in a way that's similar to dynamic programming, but because for each x, we only call this function once. So that means that this recursion thing calls all of n times. But how much time does each node take, right? Well, each node will take, there's a for loop in here, and it takes adjacency list, right? So, and well, at the worst case, there are n other edges for each node, so it'll be n squared. But if you sum up all the number of edges, because if you look at this dislike list, right? Each dislike item, each edge in the graph is represented by one item. So this is a 1-to-1 ratio, or 1-to-2 if you want to count that, but effectively 1-to-1 from one edge on the dislike graph or dislike input to one edge on the adjacency list. And each adjacency list, because for each x, and there are n of them, for each x, we only look at is adjacency list because we only call this once for each x. So because of that, if you sum up all the components of the edges, you will get the size of the dislike graph, which is e, or the number of edges. So in essence, this is a v plus e, O of v plus e running time algorithm, depending on what the vertex, or the number of vertex and number of edges. That's what the v and the e stands for. And in terms of space, it's O of v because we have at most O of, we have at most, well, okay. I guess technically it's O of v plus e, the way we did it, because we converted to adjacency list. But you could have done it another way. But so I guess space is actually O of v plus e. But if you were maybe able to, or wanting to do it a little bit smarter, then you could do an O of v time, or O of v space, sorry. But in terms of running time, you cannot do better than O of v plus e, and that is what we call the lower bound, because O of e in this case, even though e is strictly less than, not strictly, but it can be less than n squared, which is the upper bound for v, at least for unique edges. In that case, yeah, you have to read each edge at least once because that's the input, so that's your lower bound, and that's how we can come to the lower bound. So it's O of v plus e and time, and O of v plus e space. Okay. So the question now is, yeah, there are a couple of things. For an interview question, this is a recursion problem. This is a very simple graph theory exploration of a graph problem. So definitely I would consider it fair game for an interview. So definitely study it up. For competitive programming, bipartite graphs comes up all the time. So you probably would like to study it. Both the recursion, there's a breadth first search, and maybe union find. But yeah, definitely something I recommend. In terms of readability, I could definitely do a little bit better on the naming of certain things, but I think for the most part, and you can do this a little bit afterwards, but it's the structure is mostly okay, I believe. Cool. That's all I have for this problem, I think. Yeah. Let me know what you think. How did you solve this problem? Which of the couple of ways did you solve this problem? Did it give you any trouble? Let me know what you think. Hit the like button, hit the subscribe button, and I will see y'all later. Bye-bye.